So thanks again for that introduction. As Laura pointed out, my name is Sukrit Ranjan. I'm a Skoll postdoctoral fellow at MIT. And today I'm excited to tell you a little bit about some of my thoughts on UV light and the role it plays in the emergence and search for life in the universe. Before we get started, I just want to take a moment to acknowledge my colleagues and collaborators with whom I've done much of the work that I talk about over here. So the meeting organizers asked me to talk about prebiotic chemistry and biosignatures, which are two topics which might seem quite different at face value. Prebiotic chemistry is concerned with the question of the origin of life. Biosignatures is concerned with the question of how to look for it elsewhere. But as it turns out, these questions are related at a deep and fundamental level. Prebiotic chemistry affects biosignatures because theories of abiogenesis can provide informative priors, which we can use to prioritize scarce telescope time when we're trying to figure out which are the most interesting planets to scrutinize for evidence of biosignatures. They can also help us to provide informative priors for interpretation of a putative biosignature. If you have a measurement of a signal and you're trying to figure out whether to ascribe a biological or non-biological explanation, the biological explanation is more convincing if it's in a place where we think life can emerge and endure compared to one where it can't. But the link goes the other way as well. Biosignatures will eventually, when we detect them, play a critical role in origin of life. Specifically, the detection of life on other worlds provides the strongest lever arm we have to empirically constrain theories of abiogenesis, which was worked out very nicely in a kind of Bayesian analysis by Chen and Kipping last year. So these two questions are intimately linked, and one of the kind of mechanistic things that links both of them is UV radiation. In the rest of this talk, I hope to convince you that UV radiation plays both a critical controlling role in prebiotic chemistry, potentially, as well as, for sure, a strong controlling role in biosignature gases, in particular the questions about false positives and buildup detectable levels. I'm going to talk about UV light, so I just want to orient you what exactly I mean when I talk about UV light, and I'm going to use this excellent plot from Kevin Francis' paper to do so. When I talk about UV, I'm not talking about the XUV at wavelength shorter than about 100 nanometers. This has really important implications for processes like atmospheric escape, like we heard about earlier in this meeting. I'm also not going to be talking about the visible and near IR, which plays critical roles in planetary climate. Instead, I'll be focusing on this bit in the middle here, which plays important roles in chemistry. I just want to zoom in there and emphasize what again, orient you a little bit what I mean when I talk about UV. So this is the top of atmosphere flux for Earth analog planets orbiting the sun here in black versus the M-Dwarf GJ1214 here in red, taken from the work of Kevin Francis, 2013. This is wavelength in nanometers on the x-axis, top of atmosphere flux in photons on the y-axis. And broadly speaking, when I refer to far UV radiation, everyone sets their cutoffs a little bit differently, but when I refer to far UV, I'm talking about wavelengths shorter than 200 nanometers. This has played a controlling role in atmospheric photochemistry, in particular the chemistry of anoxic atmospheres, because it's where CO2 and H2O absorb. By contrast, when I talk about near UV radiation, I'm referring to wavelengths longer than about 200 nanometers. And those are the wavelengths that reach the surface for anoxic worlds, and so play controlling roles in superficial chemistries. You might be asking why I'm talking about UV light in the context of chemistry. The big picture is that, well, pretty much everything absorbs there. So this is a plot from Feng Tian's paper in 2014, and we see that many of the important molecules in the atmosphere absorb in this band. You might say, well, maybe that's a little bit biased, so I'm not trying to overwhelm you over here. The big picture here is that these are just a bunch of molecules that have identified as being important for biochemistry and for atmospheric chemistry. You can ignore almost everything except the numbers in red, which are the photon wavelengths corresponding to the energies of the bonds that they're associated with. And the big picture takeaway here is that photons in the UV regime affect all of these bonds pretty much. So that's the big picture reason that UV is important. And so far I've kind of emphasized bonds, so I've been kind of emphasizing photolysis, but of course that's not all that UV does. So UV can carry out photolysis, and that's a very important function, but it can also ionize molecules, so knocking off free electrons that can then go on to precipitate in further chemistry, which I'll touch on later. And it can also perform photoexcitation. So it doesn't have to break up a molecule, it can instead boost its electrons into high energy states so they can precipitate in chemistry that would then normally be forbidden. So that's kind of the big picture orientation on what UV light is and why we care about it when we think about chemical systems. So my talk is divided into 4 parts, and I've just kind of gone through the introduction. I'll next be stepping through the first part of core part of my talk, which is how UV light impacts prebiotic chemistry. Then I'll move on to UV light and the search for biosignatures, and then I'll summarize some conclusions. But first, prebiotic chemistry. What is prebiotic chemistry? Prebiotic chemistry is a study of trying to understand how we went from this, in other words, geology, a dead planet, to this, something that we would recognize as being alive. For example, this model protocell over here. As a consequence, prebiotic chemistry has two natural axes of study. One is kind of planetary science or geochemical. It's trying to understand this. What was the milieu? What was the range of environments under which life emerged here on Earth? What were the chemical conditions? What were the availability of trace compounds? Stuff like that. And that's really the concern of geochemists, of planetary scientists, and so on and so forth. And it's where I feel most comfortable, for example. The second axis is this. What was the transformation process? How did you get from simple molecules that geology makes available in bulk to the more complicated, to increasingly complex molecules, and eventually life? This, so far, is most of the domain of synthetic chemists, which I am not, but I talked to them a little bit, so maybe I can tell you a little bit about that. In the context of origin of life, it may confuse you a little bit that I'm talking about UV radiation. UV radiation in our field is typically invoked as a strong negative for life. After all, if we go outside and we get too much UV, we get skin cancer. This is generally considered negative. Kind of more directly, if you're a laboratory microbiologist and you want to sterilize your glassware, one tool you can use to do that is irradiating it with very high energy short-wave UV radiation. So in that case, how can we possibly think about UV as potentially playing a positive role? I think one key point to keep in mind is that you need to be cautious when we extrapolate from modern life to past life and indeed to the origin of life. The canonical example of this is probably oxygen. And to first order, oxygen is violently toxic. I know this might come as a bit of surprise to all of us here in this room. And because oxygen is integral for not only for us, but for pretty much all complex life here on this planet. But the reason we're able to tolerate oxygen is because of extremely complex biochemical machinery we built up. When O2 interacts with cells, and particularly when it's processed through metabolic-like pathways, it very readily gives rise to so-called reactive oxygen species. These reactive oxygen species love attacking biomolecules and essentially blowing them up. And this is why many obligate anaerobes are very vulnerable to oxygen toxicity. We have actually evolved oh dear, this is a slightly older version. There's supposed to be things like peroxidase and things like that listed here, various enzymes. So we have evolved a suite of very complex pathways to process that oxygen, and then to be able to then exploit the free energy gradients that oxygen makes available to us. And in fact, it's thought that the rise of oxygen led to the first great mass extinction by many. An even more fundamental and non-intuitive result comes in the form of liquid water. Liquid water is essential for all life as we know it. It fundamentally guides our search for life in the universe. Our astrobiology strategy is literally follow the water. So it might surprise you to learn that H2O is actually somewhat corrosive to biomolecules, and in particular to proteins and nucleic acids, because it loves doing hydrolysis reactions. This has given rise to what is the so-called water paradox, which was enunciated in the NRC report on the limits of life in planetary systems and in a review paper by Steve Benner. And what it essentially boils down to is this. If you take biomolecules, for example, this is a schematic of a nucleic acid, and you look at the lifetimes of each of the bonds that make it up in liquid water, you find that at standard conditions, they're all geologically short. They're order 100 years or less. So theories of the origin of life that rely on drip feeding in organics and building them up over mega years, that's a little bit of a problem because they won't just build up. They'll actually decay on a relatively short timescale. And so this is the so-called water paradox. It's also why organic chemists, when they perform their syntheses, typically use organic solvents, not water, which I recently learned has prompted a quote, sustainability crisis in organic chemistry. And it's also why even grizzled organic chemists don't immediately laugh us out of the room when we talk about life in organic solvents on Titan, because truth be told, many of them are trying to design life from the ground up. They might not use liquid water either. So the key takeaway from here is it's not as simple as saying, is this good for life or bad for life? Everything has good aspects and bad aspects. You have to ask, does the good outweigh the bad? And i.e., does the constructive chemistry dominate or the destructive chemistry? In this, viewed through this lens, UV starts looking a little bit different. So there's kind of three broad families of reasons to think that UV light is relevant to the origin of life. The first is experimental and stretches back, I think at this point, 6 decades. And it's the fact that in the laboratory, UV light has been shown to drive a diverse range of synthesis. It can form each of the major classes of biomolecules, i.e. sugars, nucleobases and nucleotides, amino acids, lipid precursors. It can also drive a number of processes, including oligomerization, and so on and so forth. One of the pathways that I'm most excited about is that UV light is integral to the only pathway for the selective high-yield synthesis of the ribonucleotides, the main fundamental components of RNA. And UV light is utterly key to that in ways that I'll touch on just a little bit later. So that's experimental. It works in the lab. There's also a theoretical argument. Not only was UV light the most abundant source of chemical free energy to the surface of early Earth by several orders of magnitude, it also turns out that because that UV light arrives quantized right at the energy of those molecular bonds, it's capable of directly affecting changes in the electronic states of molecular systems. In other words, it's capable of affecting irreversible changes in the entropy of molecules. It's capable of kinetically trapping them in ways that other sources of energy, like thermal energy, can't do, because there's always a reversibility problem there. And that was worked out in a very nice paper by Robert Pascal in 2012. But perhaps the most compelling piece of evidence is historical. There's a long body of work here, but I think it reached its apotheosis so far in work by Ashley Beckstead in 2016. What this is a plot here is of the UV resistance of different nucleobases. So if you shine light on a nucleobase, will it blow up or not? The blue squares over here are the nucleobases that life uses, the biogenic nucleobases. The red circles are nucleobases that life doesn't use. There's a whole bunch more of these red ones way over here, but that they didn't bother to show because you're getting the picture already. This is a log scale over here. The lower you are, the more UV resistant you are. So something here is 10 times more UV resistant than something here. And we see that the biogenic nucleobases are united in being extremely resistant to UV attack. They have extremely efficient non-rated photoexcitation pathways, photo de-excitation pathways, which has been evidence that they at least evolved in a high UV environment. Okay, so UV light might be relevant to the order of life. People have fleshed this out a lot in past decades, but this fundamental idea has been around for a little while. So people have been thinking about it for a little while, and in particular asking the question, what exactly was the nature of the UV irradiation on early Earth? To my knowledge, some of the first work on this was done by Charles Cockell back at the turn of the century. And the key result that came out of his work was that if you just kind of take fiducial models of the early Earth's atmospheric state and plug them through a radiative transfer model, you essentially get nothing at wavelengths shorter than 200. And that's because of atmospheric CO2 that really robustly absorbs there. You might say, well, that's all well and good, but that's a fiducial model. There's a lot of uncertainty about the early Earth's atmospheric state. How can you be sure that's the case? And the reason we can actually be relatively certain that's the case boils down to the existence of atmospheric CO2. So we know that there must have been a certain minimum amount of CO2 in order to solve the faint young sun problem. The minimum amount of CO2 that's allowed in the climate models comes from the work of Wordsworth and Pierre Humbert. It's if you have a ton of N2 in the atmosphere, you can have as little as 800 microbars of CO2. And that's shown here in this, what color is it on this one? Oh, it's purple here, great. In this purple line over here. So this is showing the UV surface environment for early Earth, assuming 0.9 bars of nitrogen and varying amounts of CO2. The black line is what the young sun was putting out. This line is 800 microbars of CO2. And we see that even with this low CO2 inventory, we've already essentially put in place that 200 nanometer cutoff. So even at the minimum amount of CO2, you don't get anything short of 200. Most other components of a planet's of early Earth's atmosphere that we think were there, like H2, N2, CH4, H2O, they all absorb over here. You can't get blood from a stone. Those photons are already all gone due to CO2. As a consequence, we're not sensitive to the uncertainty in those parameters, although it is considerable. So we don't care about that degree of uncertainty. What about the other extreme? This is the minimum amount of CO2. The maximum amount of CO2 we could reasonably have is given by this red line over here. That's if you have 70 bars of CO2 in the atmosphere. It's what you get if you volatilize the entire crustal carbonate inventory of the Earth as CO2. So it's kind of an extreme upper limit, but it is an upper limit. So you can think of this as kind of being the minimum amount of UV. And you see that this curve and this curve aren't actually that different. And that's because CO2 saturation sets in relatively early in the absorbing regime. Longward of 2 or 4 nanometers, you only have scattering. And their transmission drops off only slowly with optical depth because it's purely scattering. So as a result, we have a pretty good sense of this particular initial condition, which is consistent with available geochemical constraints like Smith. Interestingly, this is also in concordance with the results of some experiments. My colleague Zoe Todd has started a program where she takes some of these UV-dependent prebiotic pathways. They're pretty much almost all measured in the lab using a monochromatic source. So she asked the question which many planetary science think is obvious, but is not obvious in the bio community, which is what is the wavelength dependence of these pathways? Could they work under realistic UV? And she finds that she's only looked at a few of these pathways so far. It turns out lab work is hard. But in the few pathways she's looked at, she's found that broadband UV, pretty much every wavelength longward of about 200 to 10 nanometers works pretty effectively, all the way up to about 300, at which point it starts dropping off. You're not getting enough juice to get the thing going. Intriguingly, and this is much more tentative, so far in the pathways she's looked at, the far UV wavelengths shorter than about 210 nanometers, tend to be strictly destructive. So At these kind of moderate UV, what I call the near UV regime, you get constructive chemistry. And at the far UV, at least in the few pathways she's looked at so far, she's gotten strict destruction. So that aligns relatively well with this atmospheric window. So that's nothing serious yet because we've only evaluated a few pathways, but it's something we're continuing to look into. And the story is pretty similar for early Mars with the caveat for dust. So you have this UV. What exactly can it do for you? It turns out there's a whole bunch of stuff, but I want to focus on the role UV plays in potentially solving one long-standing problem that's been around ever since the planetary scientists told the biochemists prebiotic chemists that they weren't allowed to have a super methane-rich early Earth atmosphere, and that's a question of reductance. Most of the carbon that volcanoes put out comes in the form of CO2. Most of the carbon in biomolecules is reduced. How do you reduce it in the absence of atmospheric reductance? So this has been a puzzle for a while. A few years ago, it was proposed that one potential solution to the puzzle came from UV light. And specifically, the idea is if you take hydrogen sulfide, HS-, copper as a catalytic counterpart, and UV light and shine them together, you generate solvated electrons. And solvated electrons are literally a minus charge floating around. It is literally reducing power. And it's because it's just a free electron, it's actually quite reactive. It can go off and reduce all sorts of things. And so this was a solution that was put forward for how do you get reducing power in a comparatively oxidized early Earth environment. There's a couple of problems with this scenario. One is its reliance on copper as a catalytic partner, because copper is geologically rare and not very plausible. The other is that it's actually not very efficient. In particular, it doesn't work under early Earth UV, which is something that Paul Rimmer figured out when he tried to simulate realistic environments in the lab. However, as planetary scientists, we know that sulfide is not the only S carrier on Earth. In fact, it's not even the major one. Most S comes out of volcanoes as SO2. And in the absence of oxygen, that S will then dissolve into liquid water. It'll dissociate to form sulfides, the sulfites, SO3 2-, HSO3-, and so on and so forth. And if you just do a very simple model of that process for shallow ponds, you find that prebiotic ponds should have been sulfite rich, concentrations of 10 micromolar or higher. And we had a discussion with this about our prebiotic chemistry colleagues. I don't know when those guys sleep because we had our conversation around 4 p.m. and we had preliminary results the next morning. They essentially plugged, they work real hard over there. They plugged it into their prebiotic chemistry pathways, and the net thing that they found is that not only does sulfite work, it works a lot better. It works with it works under realistic UV radiation, so it provides those electrons at the right pace, and it works with iron as a catalytic partner, not copper. And that's important because iron is much more prebiotically plausible. So you get 2 improvements for the price of 1 here. So that's one way in which UV can really help and solve kind of some of these long-standing problems. However, UV giveth, UV taketh away. And in particular, because UV is delivering so much chemical free energy, it's doing all sorts of things. One of the things it's doing is it's controlling the inventory of UV-sensitive molecules at the surface of the early Earth. And this is important where it comes to the nitrogen question. Biomolecules incorporate nitrogen. We do have a ton of nitrogen. It's floating all around us as nitrogen gas. But as Colin told us earlier in the meeting, that nitrogen gas on its own isn't very helpful because those nitrogen atoms are connected by that high energy, really strong triple bond. It's really hard for even modern life to break apart that bond. Light nitrogen is often the limiting ingredient in modern biology. And it's even harder to figure out how you could do that abiotically. One mechanism that's been proposed over the last 3 decades is lightning. The idea that if you had lightning in an N2CO2 atmosphere, that should be able to jazz apart that N2 and that CO2. The N's and the O's can then combine and form NOx, which can then rain out and potentially accumulate in prebiotic reservoirs. This is an idea that's been simulated with increasing precision over the past few decades, culminating in a recent couple of papers, which predicted the concentration of these molecules should reach up to 10 millimolar. For reference, the modern NOx concentration in the bulk ocean is 50 micromolar. So people were predicting that you get 200 times as much NOx in the early ocean in the absence of biological carbon nitrogen fixation compared to the modern ocean. And this would be correct if the sun didn't have any UV emission. The challenge here is that what people hadn't included before is the fact that UV light is robustly known to photolize nitrate and nitrite in natural waters. This is observed in situ and it's also observed in the lab. If you include the effects of this rate constant, you find that the oceans could never have built up prebiotically relevant, by which I mean more than 1 micromolar concentrations of NOx. This is a sink that's about 3 to 5 orders of magnitude stronger than the earlier sink, which was processing at deep sea hydrothermal vents. And this mechanism would probably keep fixed nitrogen concentrations low in most bodies of water. They could get to be high in a very particular scenario, that is to say specifically in shallow ponds with large drainage ratios. And the idea there is that if you're delivering your nitrogen from the atmosphere, if it's shallower, you dilute the atmospheric supply over a thinner column. And if you have a large catchment area, you can integrate runoff from a larger area. So maybe you can get more NOx that way. And if you have such a favorable pond, then you can access prebiotically relevant concentrations of nitrate and nitrite. So this is a theoretical prediction. I was kind of expecting it to be a theoretical prediction for a while because minerals of nitrate are very, very soluble. However, nitrogen in organic gunk is not very soluble. It turns out that one of the messengers we have about ancient nitrogen is in the form of kerogens. And there was a group that last year published a paper analyzing kerogens from 3.2 billion-year-old kerogens, organic gunk, from both oceanic and lacustrine lake environments. And they identified a signature in the nitrogen isotopes in the lakes that was consistent with nitrogen fixation in some of the lakes. With denitrification in some of the lakes. So it seemed like microbes were eating nitrate over there. However, they did not identify that feature in all the lakes, nor did they identify it in the oceans. So the implication of this is that some lakes and ponds on early Earth were prebiotic Earth were nitrate rich, but not the oceans and not all ponds, which is in broad consilience with our scenario. So we're kind of excited about the prospect that maybe we can test these predictions more rigorously later. But so far I've talked to you only about planetary science, and this is ExoClimes after all. Let's go to a different planet and ask how things change. In particular, let's go to M-Dwarfs. The gospel of the M-Dwarf has already been presented in this meeting, so I won't belabor it in too much depth. But just as a quick reminder for some of our colleagues who may not be as familiar with it, you are being preached to. M-Dwarfs are a really interesting class of star. They're stars that are smaller, dimmer, and cooler than our own sun. They're the most common type of star in the galaxy. Studies from Kepler show that potentially habitable planets are common around them. A statistical finding which has received experimental validation with a number of individual planet discoveries, like that of the TRAPPIST-1 system, which contains 2 to 3 potentially habitable planets, which is quite exciting. In addition, they're the only possible targets for near-term atmospheric characterization over at least the next decade or two. That's just because M-Dwarfs are small, so the relative spectral amplitude of atmospheric absorption is much stronger around these objects. So they're the most common potential home for life in the universe, as Ray alluded to in the introduction to this meeting. They're the only place we can look for life beyond Earth. And of course, so this has fueled a robust debate about whether life can emerge and endure on these objects. This debate has many axes, some of which we've heard about earlier in this meeting. I'm going to focus on just one part of this debate, which is the UV environment and then the implications for the emergence of life. 50 minutes actually isn't that long, so I'm going to skip the buildup and just go straight to the conclusions, which is that M-dwarf planet surfaces are UV poor. So what this is showing, this is essentially showing here is a surface UV radiation environment on M-dwarf planets. You have wavelength in nanometers on the x-axis, the surface radiation in photons on the y-axis. The black line is what you had access to on early Earth, and the colored lines is what you'd have access to on an early Earth analog planet orbiting these M-dwarfs, so filtered through that 1 bar N2 CO2 atmosphere. And I should point out that the data sources here are primarily from the muscle survey, but also from the virtual planetary laboratories online compendia. And the key takeaway here is that M-dwarf planet surfaces are UV poor because longward of 200 nanometers, which is the only thing that makes it to the surface, the radiation is formed in the photosphere. M-dwarfs are cool, so they have much less photospheric UV. So that's all that's going on there. We can quantify this a little bit by computing the reaction rates for prebiotically relevant processes. And we can say that overall abiotic M-dwarf planets have about 2 to 3 orders of magnitude less bioactive UV than prebiotic Earth. This has real implications for potential prebiotic chemistry. And it's not just you wait 100 or 1,000 times longer, because you always have thermal back reactions. So your photochemistry needs to be building biomolecules faster than your thermal chemistry destroys them. So there's a threshold amount of UV. And if you don't exceed that threshold, UV-dependent prebiotic chemistry may not proceed. Paul Rimmer, in collaboration with others, including Didier Close and John Sutherland at the University of Cambridge, has started looking at this question. He's looked at it for a couple of pathways in particular, and he's shown that ribonucleotide synthesis pathway I told you about, the only one known for their high-yield selective synthesis, can't operate under steady-state M-dwarf UV, which has given rise to what Paul calls the abiogenesis zone, the idea that maybe high-mass stars are much more clean places for life to emerge. There's one glaring caveat here that I can tell half of you are sitting on your hands about, and that's flares. M-dwarfs are flare stars. They flare frequently, they flare often, and when they flare, they go from putting out less UV than the sun to putting out more UV than the sun, which raises the question, can intense but transient UV from flares substitute for high steady-state UV? This question is being addressed both observationally and experimentally. Sorry, this is a little bit out of order. Observationally, folks including Max Gunter at MIT are using tests to do flare frequency distribution studies of M-dwarfs, trying to figure out how much they flare and how much energy they put out. And their preliminary findings so far is that maybe 10% of M-dwarfs put out enough energy to compensate. And Paul Rimmer, as I mentioned before, is leading experimental studies to figure out can the proposed prebiotic chemistry use this intensive radiation? Can it compensate? If the answer to this question is yes, it provides a rare positive tick for the habitability of active M's, so it provides a positive entry into that ledger. If the answer is no, I think that's the most exciting case of all, because it constitutes a testable prediction. If this pathway is required for the emergence of life, if UV light is essential for the emergence of life, then you shouldn't find life on planets orbiting M-dwarfs. So if you find biosignatures there anyway, you can falsify this theory, which is lovely. So that brings the prebiotic chemistry part of the talk to a close. The key takeaways are we have a pretty good sense of what early Earth and early Mars UV was like. It's broadband north of 200 nanometers. This can power a lot of constructive chemistry, and in conjunction with sulfide can solve the long-standing reduction problem. It controls other aspects of the surface environment as well. In particular, it controls the abundance of NOx, of fixed nitrogen on the early Earth, and restricts you to ponds if you really want a lot of that. Prebiotic M-dwarf planets are a little bit different because they have a lot less UV. This is potentially quite exciting. We first have to figure out if flares can compensate. Flare UV can compensate for steady-state M-dwarf UV. If it can't, that's really exciting because you can potentially use exoplanet observations to constrain origin of life theories. This segues me really nicely into the next part of my talk, which is how are we going to find life on planets orbiting other stars, UV light and biosignatures. Before I jump into this, I want to take a moment and pause about the magnitude of the opportunity exoplanets offer us. It's not just that there's so many potentially habitable exoplanets, potentially hundreds or thousands that we can hope to, potentially hundreds that we could hope to observe if we get good enough telescopes. It's this. Each and every planet is a prebiotic chemistry experiment. It's a prebiotic chemistry experiment running at scale. Thousands, tens of thousands of square kilometers, a wide range of conditions and cycles operating over geologic time. We can never do prebiotic chemistry experiments as well as planets can. And if we can just read the outcome of those prebiotic chemistry experiments, we can gain really fundamental insights into the nature and into what might be laws of biology. Exoplanets offer, this has been quantified in a abrasion framework by Andy Sandberg here, and by Kipping and Chen, and by Lingam and Loeb a little bit. And the essential thing that they point out is that if you detect even one biosphere beyond Earth, you strongly constrain many theories of abiogenesis. For example, one still extant debate is contingency versus inevitability of origin of life. Are there processes out there that inevitably drive chemical complexification in the emergence of life? Or did a bunch of molecules one day just decide to quantum tunnel together and give us LUCA? We can't actually exclude the latter right now, even though we don't like it very much. The detection of even one biosphere would rule strongly on that. Beyond Earth would rule strongly on that. And similarly, if we can detect a few, then we can start making broad statements about what conditions fuel the origin of life versus disfavor it. Exoplanets are particularly outstanding here because they're an opportunity for an uncontaminated experiment. I love the solar system bodies. I love each and every one of them. They have fundamental things to teach us, and if we detect life there, it'll be an amazing discovery, and it'll tell us a lot about habitability. But it won't necessarily tell us about the origin of life, particularly if it has a biochemistry similar to ours. And that's because of the risk of terrestrial contamination. We know that terrestrial bodies swap rocks back and forth. We know this from the existence of Martian meteorites. We know that the interiors of those meteorites experience climate conditions not exceeding 40 Celsius. And we know that from N-body simulations, for example, by Wirth et al. At Penn State, that Earth has transferred on the order of a megaton of matter to the icy moons alone, and much, much more, of course, to Mars. So there's a real risk of terrestrial contamination. If you detect life there, you can't be sure that it wasn't exchanged back and forth in the solar system. Exoplanets avoid that problem. So it would be super great to detect life there. So how are we thinking about doing this? The essential paradigm is right now we are discovering potentially habitable, probably rocky worlds. Today we can spectrally characterize the atmospheres of large planets and see what's in them. In future, we hope to do the same with smaller rocky planets and scrutinize them for evidence of life. What do we mean by evidence of life? To think about this question, we can go back to the granddaddy of them all, the only time this has actually been tried, which is a very clever experiment by Carl Sagan and his collaborators back in 1993. So when Galileo was on its way out to Jupiter, it swung by Earth on the way. So they just had a very simple idea. They stuck out all its instruments, they trained them on Earth, and they tried to see if they could remotely detect evidence of life on Earth. It was not as straightforward as you might imagine, as long as you exclude things like TV signals. That is a bit of a gimme. But the most robust evidence that they found for life on Earth was essentially in this plot over here. This is a spectrum of the terrestrial atmosphere, and they detected a number of molecules at relatively high concentrations. So they detected O3, which is biogenic, but that's not a good evidence for life because there's a robust UV difference false positive. If you UV irradiate an O2 atmosphere, you make O3. Not convincing. They found O2 and N2O, which they were more excited about, but again, there were significant false positive risks, and they concluded that they couldn't conclude that life was there based on that alone. What did eventually convince them was the existence of CH4 in an oxic atmosphere. CH4 is known to be biogenic. It was also present at an abundance about 140 orders of magnitude out of thermochemical equilibrium, so that was weird. It should have had a lifetime of about 10 years, which meant that kinetics should have been able to restore that equilibrium very quickly. So something must be pumping it up and maintaining it. They went through the list of abiotic processes they knew about, which would make CH4, concluded that none of them could maintain the required flux, and concluded that Occam's razor forced them to conclude that there was life there. So this is a kind of analysis that one day we hope to do with an exoplanet. It's very context dependent. In terms of oxic atmospheres, the biosignature that they identified, CH4, O2, and ideally H2O, remains probably the most robust one we've come up with so far. The challenge it really faces is one of observation. First, you kind of have a trade-off between oxygen abundance and methane abundance over Earth history, as Olson et al. 2016 and Reinhardt and colleagues in 2017 pointed out. Either you have high methane, so it's easy to detect, or high oxygen, typically not both. You also have kind of more fundamental observational challenges in that, for example, O2 absorbs at relatively short wavelengths. CH4 absorbs at relatively long wavelengths. So you need different big observatories to be able to detect them. And with CH4, you also run into the problem that CH4 absorbs like this, so does almost every other hydrocarbon. So you have to figure out how can you discriminate those guys apart. So I'm not saying that this is a bad biosignature, by far the opposite. We should definitely look for this. But these are some of the reasons people have kept on thinking about this problem a little bit. So what would an ideal biosignature gas be? Well, obviously it would be biogenic. It would be produced by life. For example, the way oxygen is produced by phytoplankton here on Earth. It would be spectrally distinguishable. We should be able to clearly tell it apart from other molecules that might absorb in the same region of the spectrum. And it should have no abiotic false positives. We want life to make this, not rocks. Finally, we would like it to be detectable. We need to be able to accumulate to detectable concentrations on inhabitable planets. Both the UV light comes into both of these questions. See these second two questions over here. That's the work that I've been doing, and that's a little bit of what I'll share with you today. I can't talk about biosignatures without talking about the granddaddy of them all, O2. O2 is an excellent biosignature in many ways. It's biogenic, it's detectable, it's distinguishable, it has an excellent terrestrial motivation. But the big risk of it is that it has a lot of false positive possibilities, driven by both photochemistry and escape. Photochemistry is a little bit less of a concern now, thanks to the recent work of Sunny Harmon, showing that the products of lightning suppress this false positive signal. But the escape-driven false positives remain. And the fundamental picture that it all boils down to is you can come up with scenarios where you have water vapor, which is present on habitable worlds, and you can come up with ways that water vapor can photodissociate, the H can escape, the O remains, and so you build up an abiotic O2 layer. And all of the escape scenarios basically boil down to that. There's ways you can discriminate out some of them, as was shown by Eddie Schwieterman in a 2016 paper. And the idea is that, for example, if your O2 is due to CO2 photolysis, you should have lots of CO, so you can look for that. Alternatively, if your if you have a lot of O2, like 100 bars of it, driven by the escape of an ocean, catastrophic escape of an ocean, that should produce O2 dimers, which you can also look for. But there's a big regime in the middle where we can't necessarily discriminate out all those false positives. So that's a potential challenge. So that's a potential challenge with O2. This is in fact a potential challenge with all the quote-unquote simple molecules, the molecules that it's relatively easy for life to make. That's because the molecules that it's relatively easy for life to make are also relatively easy for non-life to make, for abiotic processes to make. Nature can exploit the same basic thermal free energy gradients that life can. So this has motivated people to think a little bit about hard to make molecules that it's really hard to make, that you would seem to uniquely need life biological enzymatic machinery to make. People have mostly thought about this in the context of anoxic atmospheres, because these hard to make molecules also tend to be reactive. And the idea is that oxygen is purely reactive. Anoxic atmospheres are hopefully less reactive and better places for these gases to build up. This also has a very robust geological motivation in the sense that for about half of Earth's history, it was anoxic. So if you don't think about anoxic atmospheres, you will literally throw out about half of your potential biospheres. The first work in this regard, to my knowledge, was done by Sean Domingo-Goldman's group back in 2011. And what they did is they looked at the organosulfur, CH3 DMS, DMDS, and so on and so forth, as potential biosignatures. These are the product of sulfur-based biochemistries. Their essential finding is that these are really good biosignatures in many ways. In particular, they don't have false positive risk, but you need very high fluxes in order for them to become built to detectable concentrations in the atmosphere, and that's UV limited. And they felt that such high fluxes were unrealistic. We think that this approach overall is a very sensible one. So over at MIT, William Baines, Janusz Kwiatkowski, and Sarah Seeger are leading with what we call the All Small Molecules Project, an effort to look at all the things that life makes and evaluate them as potential biosignatures. This is a bit of an undertaking, given that even after our initial course cuts, you still have about 10,000 of them. But we're pleased to report that the first results in this program are finally starting to roll in. The first gas I want to tell you a little bit about today, adding to that inventory that's already been built, is PH3, phosphine. PH3 has a number of appealing characteristics as a biosignature. It has strong detectable spectral features. You can tell it apart. And I should mention, this is work being led by Clara Sousa Silva. This has strong detectable spectral features. You can tell it apart from a lot of other molecules. It has no known geological false positive mechanisms, and we looked at a lot of them. Its Achilles heel, as with the organic sulfurs, is that it's really efficiently photochemically destroyed. And we figured that out by calculating the concentration of pH in the atmospheres of various kinds of exoplanets as a function of total pH3 flux to the atmosphere. That's what's shown in these spaghetti plots over here. Thank you, Tom, for that name. And so let me just this is kind of one of our core results, so let me walk you through it a little bit. Here I'm simulating kind of the optimum detection case, an H2-dominated atmosphere orbiting an M-Dwarf star, so that's the kind of easiest thing we could hope to detect. The x-axis here is molar concentration. The y-axis is altitude in kilometers. The solid lines refer to an atmosphere forced by 10 to the 10th molecules of pH3 per square centimeter per second, and the dashed lines by 10 for 10 to the 11. pH3 ends up being detectable at 10 to the 10 in emission and 10 to the 11 in transmission. So these numbers have no context. How can you tell if this is big or not? Oh, well, for reference, the modern methane flux is 10 to the 11. So what this means is, in order for pH3 to be detectable, it needs to be a primary product of the biosphere, emitted at the same rates that methane is. So this biosphere needs to have chosen to make pH3 at the same rate that our biosphere is choosing to make methane. There are scenarios in which we can envision this happening, particularly acidic, anoxic, and warm environments, but this is by no means guaranteed. So the punchline here is, if you see pH3, it's a pretty good sign that you've got life, but you shouldn't necessarily go out and bet the house that you'll find pH3. The situation is pretty similar for isoprene. So isoprene is a relatively big hydrocarbon. It has the advantage that, unlike pH3, it is a massive product of biochemistry. It's emitted at the same mass flux that methane is, and it's emitted by almost every kind of light. It's emitted by microbes. It's emitted by trees. It's emitted by us. Pretty much everything gives off isoprene. It's very deeply rooted in the tree of life. It's spectrally detectable, with a giant glaring caveat that it's easy to confuse with CH4, so you need to be careful in your observations in a few bands to make sure you can distinguish between CH4 and isoprene. And it has no known false positive mechanisms, but it's even more photochemically reactive than pH3 is. And you'd need on the order of 10 to the 12th molecules per square centimeter per second to detect it. So you need your biosphere to be producing it at about a rate of 20 or 30 times that our biosphere produces isoprene today. So not completely implausible, but also not something you'd bet the house on. So it's worth checking for, but not worth betting the house on. The key thing that jumps out to us in both of these scenarios is that M-dwarfs are really an ideal detection case. All of these gases are able to build up to much higher concentrations on planets orbiting M-dwarfs because M-dwarfs are low UV environments. And the main control on the concentrations of all of these gases, directly or indirectly, are UV. Directly, UV can directly photolyze these molecules, but indirectly, UV will anyway photolyze molecules like CO2 and H2O, and the radicals they generate will then wander around and blow up these molecules as well. In fact, for these molecules in the scenarios we simulated, radical loss was the main loss mechanism. And ultimately, that is controlled by the UV environment. That's just that's illustrated in so this is a result that is similar to what Segura et al. 2005 found for CH3Cl and CH4, and this is just an illustration of that. This here I've simulated pH3 buildup in 2 exoplanet atmospheres. The parameters are identical except that one of them orbits a sun-like star and one of them orbits an M-dwarf. And we see that in the case of the M-dwarf, it goes much higher, so better for transmission, and it builds up to a few orders of magnitude higher in concentration. So M-dwarfs remain an ideal detection case. The cult of M-dwarfs continues. So to summarize the key takeaways from the biosignatures part of the talk, the gold standard biosignature, if you can detect it, remains O2, CH4, and H2O. If you're not able to detect it and you're looking for a single gas biosignature, for example, because of the O2, CH4 trade-off, the simple molecules like O2, methane, N2O, and so on and so forth are excellent detection prospects, but they have a substantial false positive risk because nature can make those molecules relatively easily as well. The complicated molecules like CH3, organosulfurs, pH3, and isoprene have low false positive risk, but you need very high fluxes in order for them to be detectable. And it's not clear yet whether or not that's plausible. Only observations will tell in the end. In all cases, M-dwarfs remain optimal, not just for their small sizes, but because of their small UV fluxes, which means that it's easy for these gases to build up to high concentrations. So to bring the talk back to the questions that motivated it, we wanted to understand a little bit about prebiotic chemistry, biosignatures, and the connection between them mediated by UV light. These are giant fields of inquiry in which I've only touched necessarily in a few small parts of it. So if you have more questions, I hope you'll ask them. You'll ask in the Q&A. But to summarize the parts of it that I talked about in terms of UV light and prebiotic chemistry, UV light plays a controlling role in the prebiotic environment. It controls the buildup of the environmental reagents that could power the emergence of life. In particular, it restricts NOx to strictly to shallow ponds. So if origin of life does require NOx, it'll have trouble working in an ocean, but it might work in a shallow pond. So we should think about those environments a little bit. If you do have that UV, it can also do great things for you. It can power a wide range of synthesis pathways. In particular, in conjunction with sulfite, it can solve the reduction problem. And M-dwarfs are a really exciting test case in this regard because they're low UV environments, which means that we might be able to use them to test theories of abiogenesis. In terms of UV light and biosignatures, UV is important here because it's the ultimate control on the buildup of potential biosignatures in planetary atmospheres. Biosignatures, we divide into two categories. One are the simple molecules, which tend to have high false positive risk, but are very detectable. And the other category are the hard-to-make molecules, which have low false positive risk, but you need very high fluxes to detect them. And it's not clear that biology will choose to make that choice elsewhere in the universe. In all scenarios, UV controls the buildup. As a consequence, M-dwarfs remains the ideal place to look, both from the perspective of constraining theories of abiogenesis, and also just from the perspective of being able to make that constraint in the first place, of looking for these biosignatures. That's about all I've got. I'd like to thank my colleagues, collaborators, and especially my funding source, the Simons Foundation. I'll leave my slides up, and I'd love to take questions.
Thank you for that talk. And while the mics are going around, I wanted to take the prerogative to ask the first question. And it's about flares. So you said that the UV controls the buildup of the isoprene and the pH3, but then if the steady state is too low to actually destroy them, but then the flares would have destroyed them because of the increase of the UV flux, but is the time scale like not enough that it can continue building up, or like what?
That is a great question, and that's something we'd like to address in future work. What is the effect of time variable phenomena such as flares, and not just the UV, which from work by Matt Tilley and Antigona Segura might actually be relatively limited, but from the particle fluxes. So that's not something that we understand yet. My bet is that it would probably not do great things for them as biosignatures, but we need to think about that in a lot more depth.
All right, thank you. All right, questions. If you can go to Yamila.
Hi, I have a question regarding pH3 as a biosignature. You were using hydrogen-dominated atmospheres for those calculations, but you create a lot of pH3 without any biology involved in a hydrogen-dominated atmosphere. So how is that a biosignature?
Not under habitable conditions, you don't. The formation of pH3 in H2-dominated atmospheres is not thermodynamically favored at temperatures lower than about 800 Kelvin. In the case of the gas giants where pH3 is detected, it's thought that it's upwelled from deeper regions of the atmosphere where the conditions are a lot higher temperature and a lot higher pressure.
Can we do down here in the front?
So if I understood your points correctly, you need UV light to power some of those prebiotic chemistry and basically as an energy source. But then I think you're also telling us that M-Dwarfs are particularly good because you don't get too much UV. So do you foresee there being like a, I don't know, maybe not a fine-tuning problem, but a sort of a, how precise do you have to be just enough as an energy source, but not too much UV that you're basically killing your prospects for?
So I argue that the better way to think about this is not, let's assume we understand how life forms and then try to figure out, like, we can think about that a little bit, but I think M-Dwarfs are so observationally favored in so many ways. They're the ideal test case in so many ways. We're going to look for life there anyway. So if we should instead ask, what can searching for life about M-Dwarfs tell us about theories of abiogenesis? So we're going to make the measurements anyway. I prefer to ask, once we make those measurements and we find results, what can the positive or negative detection tell us? A positive detection potentially has the opportunity to tell us that UV light is not required for the origin of life, and we need to go back to the drawing board in a lot of this, which would in of itself be quite exciting. A negative detection, well, I guess a negative, yeah. Well, there might be UV light might have helped here, but like it wouldn't rule on that. It would at least tell you that UV light is not essential. By contrast, a negative detection, if you keep finding negative detections and you do find life elsewhere in the universe around higher mass stars, that would be a hint that UV light is essential. So I prefer to think of it in the other way around.
So you don't think both of your points can be correct then? Because they seem to be then contradicting each other, if I understood you correctly.
I think that this is a big and complicated question, and we should try to work at it both ends if we can. And again, like the priors that I have going into this, from what I understand of the chemistry aspect of it, I do favor a little bit the idea that UV light is essential. So if you ask me to put my money on it, that's what I would bet on. But my opinion doesn't matter. Nature's opinion is what matters here. And what is important to me about exoplanets is that it's an opportunity for nature to tell us how she prefers to work.
Colin?
I've got another question about phosphine, which is why, if we had life anything like Earth life, why would it make it at scale? Because phosphor is an essential nutrient, and there's few, with the possible exception of using methylated compounds to transfer some nutrients from the ocean to land, where they're abundant in the ocean and not abundant on land. But phosphorus is abundant on land and not abundant in the ocean. So why would we put it into gas form to get rid of it?
I don't know, but the fundamental answer is life does it anyway, so we should deal with that. In particular, I think one of the questions you're asking is there detection of phosphorus production? And the answer to that question, broadly speaking, seems to be yes. Phosphorus keeps being detected over environments that are anoxic and a little bit warm. For example, it keeps being detected over systems like sewage plants. It's detected from the flatula and the exhaust of various animals, so it's coming out of intestinal tracts. It's detected, and it's also been detected in the laboratory context where people have taken these microbes, grown them on phosphate, and it seems to have converted most of it to phosphine. So it seems that life has chosen to do this, and we should maybe try to figure out why. I should mention that Janek Petkowski has some ideas here, in particular under warm acidic conditions, reduction of I don't know the details on this, but in his paper, he argues that reduction of phosphate to phosphine can liberate free energy, so it's potentially an energy source if you have phosphate available. And he also thinks about it in the terms of a signaling mechanism. But I would defer to Janusz on that one. I don't know the details of that aspect of it.
RJ up in the back.
You mentioned high fluxes of mass between planetary bodies in the solar system and how that kind of might prevent them from giving us much information about abiogenesis if we found something on like an icy world or something like that, because it might have come from Earth. But do we have any good idea about the flux of mass between stellar systems? For example, like if we found life on a planet orbiting an M-Dwarf, how sure could we be that it hadn't just panspermed from somewhere else?
That's a really great question. I actually think someone has worked out the numbers on this, but I don't remember the citation. So I guess you'll have to take what I say with a grain of salt. My understanding is that it has been quantified and it's a very low risk of transfer, a very low rate of transfer, but I don't remember the reference, so I can't say that for certain.
Yeah, he likes that idea a lot.
And then over the wall to Sarah.
I have a a quick question and a quick comment. I'll do the comment first. I just wanted to emphasize what I presented yesterday, that we're seeing organosulfur compounds in our experiment being abiotically produced. The question is, if you favor UV mechanism to produce nucleobases, I was intrigued by the fact that you decided to completely ignore photons short of 100 nanometers, because if you're going to make nucleobases in a nitrogen-dominated atmosphere, you have to break the nitrogen somehow, and you need photons shorter of 100 nanometers. So did I miss something?
So there's two really great points here. One is, I think it's a really great point about the organosulfur production potentially high up in the atmosphere. I think it would be really instructive to gain a quantification of the amount of that we could expect in a natural environment, something in units of molecules per square meter per second. That's something we could plug into our models and see if that should produce a significant false positive signature. So that would be really cool to have. With regards to the second base, I think that's a really important point. We're not talking about the abiotic synthesis of nucleobases. Nucleobases are easy. You get nucleobases almost any which way. If you just take an even moderately reducing mix of compounds and even things that are not super moderately reducing, and you just blast it with free energy, if you have the ingredients available, you make nucleobases in high yield. This goes back to the classic syntheses by Aurot back in 1961. And this has been articulated in various ways. The key challenge that you have is, how do you make the nucleotides? How do you join the nucleobase to the sugar, to the phosphate group? And in particular, how do you make that intermediate bond, that high energy N-glycosidic CN bond that joins the two of them together? That's what classical syntheses that start with the puzzle, by making the Lego pieces and putting them together aren't able to do so far, because that bond is so high energy. If you inject enough energy into the system to make it, you break the Lego pieces as well. So the way this particular pathway gets around that is by cheating a little. So the key requirement that it has, the really key requirement, in addition to UV, is the availability of HCN. And there you have the CN bond to begin with. So you build the molecule around it. It's like instead of building a house and then the rooms of a house and putting it together, you start with a doorway and build the house around that. So that's the way that they've invoked so far to get around that problem.
I guess just a comment that if you want to have CN coming from the atmosphere, you have to break the nitrogen bond.
Yeah, you need either exogenous delivery, or you need some kind of mechanism. For example, photolysis of CH4 high in the altitude, or SEPs doing something interesting, or mechanisms like the ones you talked about, which is one of the reasons it would be really great to be able to incorporate those into our models.
Eric, up top.
Eric Guidance, University of Hawaii. I'll ask the question that I thought Sarah was going to ask, which is, what is the effect of aerosols or clouds on UV fluxes at the surface?
That is an excellent question. Do I have a slide on this? Maybe. Hold on. How do I escape this? Blah, blah, blah. Where is... Sorry, I have a lot of backup slides. Okay. The short form answer is that, so we looked at this particularly in the context of early Mars. The short answer is it doesn't seem to. The key thing that's going on here is that longward of 200 nanometers, both CO2 ice particles and H2 ice particles are again in that strictly scattering regime, which means that again, optical depth drops off relatively slowly, transmission drops off slowly with the optical depth. It goes as 1 over tau, not e to the minus tau. In order to significantly affect the surface UV environment, you need relatively thick cloud decks. You need to have cloud decks on the order of optical depths of 10 to 100 in order to really suppress it. And at least from the GCM models of, for example, Wordsworth et al. 2016, such thick cloud decks don't seem to be preferred.
At the front, and I'm sorry, I don't know your name.
Aurélien Wittenbach, Leiden Observatory. You mentioned some high production rate for some biosignature. I was wondering, did you check about the impact on the evolution of the atmosphere because of this production rate, for example, in terms of greenhouse or other?
No, we don't. That's because impacts are hard and we don't know how to do them. If you do, please, please, please work with us.
Ray up front.
My understanding is that phosphate is the only really biologically available form of phosphorus, and so on Earth that comes from a certain kind of mineralogy. I think it's from apatite. So how common do we expect phosphorus to be on planets in terms of delivery of phosphorus, and how special does a planet's geochemistry have to be in order to make a source of phosphate? Are there any thoughts on that?
So that's a really great question. The phosphate cycle is something that's really complicated, and I don't know very much about, to be honest, the phosphorus cycle on modern Earth. So I can't state anything with a very high degree of certainty. Let me see if there's anything I can robustly state. I don't actually think there is. Like, I think you and I both have the same basic understanding of it, which is that phosphorus is important. It's often limiting. We did check, is there enough phosphorus on the surface of, for example, Earth or in the other rocky planets in our solar system to produce these detectable signatures? And the answer is definitely yes. We don't even use a percent of it. We use much, much less. So the number of phosphorus atoms is not a limiting supply. But in terms of the more detailed geochemical cycling, anything more sophisticated, we haven't done that yet.
Yeah, and a related thing from nuclear synthesis talks I've been at, it seems that although you would expect phosphorus to be easily synthesized in high mass stars, it's actually hard to find where it's being synthesized. And there are seem to be open questions about nucleosynthesis of phosphorus.
And then RJ again.
I noticed in the list of names you gave at the very start, you had John Sutherland, and I've read some of his papers about prebiotic chemistry, and I've read some papers by this guy Bill Russell, who's a big proponent of the alkaline hydrothermal vent model, and they always jab at each other. They seem to think that each other's ideas are both just on the face of it ridiculous and implausible. So do you think the alkaline hydrothermal vent idea is dumb?
No, I certainly don't think it is. So I think that, again, opinions of people tend to be relatively useless. What's relevant are experiments and observations that will ultimately constrain these answers. I think that the Vents theory of life has many exciting things going for it, which is, among other things, it explains many aspects of modern biochemistry, for example, the role of gradients. I think that for me, the thing that really convinces me is showing something in the lab and showing that it works. So one thing that I would really love to see and I know the Vents community is working on this, is simulating some of these scenarios and showing how some of these more complex biomolecules and system cycles for which the theory has been worked out well, can be created in the lab. So that's something that would be really cool. That would be really cool to see. This should not be taken, by the way, as an implicit criticism. Why haven't they done the experiments? That's because people have been thinking about this synthetic kind of chemistry for much longer than they've been thinking about vent chemistries. So they haven't had enough time yet. So my personal perspective is that we can't favor or disfavor strongly either one yet. We need to keep doing experiments with the objective of linking it fundamentally to, in the end, something we can either measure in the lab or measure in space.
All right, let's thank Sukrit again.